Yeah, so now we're going to talk about motion in two dimensions. So now this kind of motion where we are looking at two particular components, or we are looking at two dimensions, it's an important special case of these two dimensions is what we call the projectile motion. So what happens in this part of the topic, what we'll be looking at objects which are moving in both the x and y directions simultaneously and under constant acceleration. Now, why is the part for constant acceleration important? Because remember that those formulae that we had derived last time with regards to displacement, final velocity, etc., etc. Those can only be used if acceleration is constant, right? Now, because these questions that we'll be looking at will be dealing with constant acceleration, this means that the same formula can actually be used even in the two-dimensional components. And one thing that's very, very important that you need to understand, and it's actually highlighted there as you can see, is the fact that the horizontal and vertical motions are completely independent of what of each other. So basically what this means is what's happening in the horizontal and what's happening in the vertical, they are two separate motions, and that is very, very important to understand. Okay, so now look at the diagram that we have on the on the far right. So you see there someone has thrown something that could be a bullet that's been fired, or someone throws a stone at an angle. Now what you realize that this particular stone, it's good. So what you are seeing in orange, so what you are seeing in orange, those are the x and y components. Okay, so what you are seeing in orange, those are the x and y components, and then what you are seeing in red, that's the resultant. So that's the motion that this particular object is going to take. So when it's thrown, there's a horizontal, there's a horizontal component and there's a vertical component. Those are the ones in orange, and then there is now that red, which is the resultant, isn't it? And so you see, because of that resultant, the ball, or what it could be, a ball, a stone, is going to move upwards. Right now, as it's going upwards, remember what we discussed last time. We said going upwards, there is the what? There is the acceleration due to gravity, which means that as this object is going to start going up with a particular velocity, that velocity is going to be decreasing with time, because remember that acceleration due to gravity is going to be what? Negative 9.8 meters per second squared. So meaning per second, the velocity is going to be decreasing by 9.8 meters per second. Now, so that's why when this particular object reaches its highest point or the peak of its path, you see there the velocity in the vertical. Remember, I said that the horizontal and the vertical motions are different, right? So what happens here is that when we reach that peak, when we reach that highest peak, the vertical velocity component is going to be what? Is going to be zero. Makes sense, right? Whereas, so here we're just focusing on the path. Now, what is going to happen? Now, again, after it reaches that peak, it will now start falling normally, like those previous questions that are questions that we were discussing last time, isn't it? So that's what's going to happen, and you can see that purple gravity that's being highlighted there to say, so it's going to have an effect on that stone. So that's the vertical motion. Now let's now talk about the horizontal. Now the horizontal is quite interesting more so because in the horizontal axis, okay, in the horizontal axis we don't have any acceleration. So if we don't have any acceleration, what does that tell us about our velocity? It tells us that our horizontal velocity is going to be what? Is going to be constant. And that's true for what? That's true for the projectiles, to say the velocity with which it starts, the horizontal velocity with which the object in a projectile starts with, that's the one that it will end with. Okay, the component of velocity remains constant in time. So the velocity is in the horizontal component doesn't change. Reason being, there is no acceleration, and that's what I've written there. And usually they actually may ask as an MCQ, which is a multiple choice question, to say what's the acceleration in the horizontal motion of a projectile motion. It's zero. There is no acceleration in the horizontal component, whereas in the vertical there is acceleration due to gravity. Okay, now another question which they like is okay, let's do this. So the other question which they like is, look at that diagram that's down there. So you see those different angles uh, at which an object is being fired, and then you see that the range that's being covered. So there are two things here. You see that depending on the angle at which something is thrown at, it can either have a high vertical displacement or have a very high horizontal displacement. So the question usually that they love asking, so you can see that the initial velocity is the same. It's been maintained at 50 meters per second. So now the question they'll ask you is, which of the following angles will the projectile motion have the highest range? So basically range, that's what we call the horizontal displacement covered by an object in a projectile motion. So look at the angle. You look at the angle 45. It's the angle 45 which has got the highest what? Sorry about that. So it's the angle 45 which has got the what? Which has got the highest range, isn't it? You see 45, it goes up to surpasses 250, right? So that's something that's important to take note of for multiple choices. So again here you look at again here we're trying to explain the same concept. So the velocity of the projectile changes in direction and magnitude, but its acceleration, purple arrows, remains constant. So you see the velocity of the projectile as it's going, it changes in direction and magnitude, but its acceleration remains constant. So it means that as it's going, there may be changes in the velocity. However, its acceleration is what is going to be constant. Now, acceleration in the y direction is not zero at the top of the projectile's trajectory. So the key thing is, when something is thrown up, okay, acceleration due to gravity is there, and that's what is actually going to cause the object to start falling down. If there was no acceleration due to gravity, things that go up would never come down. Okay, because because there wouldn't be gravity, right? So, but because of acceleration due to gravity, when something goes up, okay, when something goes up, the velocity will be decreasing due to the acceleration due to gravity. So that's what the acceleration at the highest point, that's why that point there is saying. So even at the highest point, acceleration is going to be due to gravity, which is going to be negative 9.8 meters per second squared, whereas it's the velocity, the y component of the velocity, that's the one that's going to be zero. Now again, remember when we were discussing vectors, we said when we were trying to figure out the equations, we are saying horizontal, it was cos theta, isn't it? And then vertical, we are saying sine theta. So that's basically the same concept. So you see there, the initial velocity horizontal, we are multiplying the initial velocity times cos theta, whereas for the vertical component, it's what? It's going to be initial velocity in the y component, it's the initial velocity times sine theta. So just basically like what we discussed in the SADs. Oh, sorry. We are from doing SADs. That's why I talked about SADs. Yeah, but what we discussed during vectors. So, uh, you would realize now something which is very, very important here is that these same equations that that we were using earlier on for the motion, we can actually be able to use them in the two-dimensional case. There's one set of three equations for each direction, right? So you see that here we can use the same equations, however, we're just modifying them in one or the other. So you see where we're saying just velocity, when we are talking about the x direction, we are what? We are actually specifying to say velocity x, which is the horizontal, horizontal motion. And then of course, because of that, because of the horizontal motion, we know that acceleration is constant. And then you can see there initial velocity, final velocity, and everything is being placed as what? As being in the x axis, which is the horizontal plane on the x or y plane. And then where the initial velocity in the x axis, as you can see there, I've circled that. That's basically what? Initial velocity times cos theta. Again, cos theta, because remember in vectors, when we're talking about horizontal, usually we use what? Cos, right? So that's something that you want to be comfortable with. And then when we're now talking about motion, which is high or rather vertical, you see the same substitutions has been done, where we are having that initial velocity in the horizontal, sorry, in the vertical, we see it's initial velocity times sine theta. Again, acceleration is constant as well, because we know that there's going to be acceleration due to gravity. Again, we can be able to find the what the speed is, and that is due to we can use the components of velocity. I'm sure you can remember this is driving us back to to vectors, isn't it? Where we've got the components of something, then we square the x component, square the y component, add them, then the square root, then we get the resultant, isn't it? And then to find the angle again, it's just a tan inverse, then um y component divided by x component, then we get our answer. So basically a revision of vectors there. So let's see again the other key components. So again, the other thing which is very important here is, I think something that I've already mentioned, that acceleration in the horizontal or in the x direction is going to remain constant, because acceleration is what? Is zero. There is no air resistance, right? No, there's no air resistance, there's no gravity in the horizontal. Gravity is always there when you're what? When you're going upwards or downwards. That's when gravity is going to act on you. So again, there again, just trying to reiterate the fact that horizontal displacement is simply going to be, so you see where there was initial velocity in the horizontal, that equation 3.13b, you see we've substituted for that constant, um, velocity. Then we now go for the equations that we use in the y direction. Here we are going to substitute. You've seen we are using sine theta multiplied by the initial velocity, and then where there was acceleration, there we are putting acceleration due to gravity, which you can see there is negative g, which is negative 9.8 meters per second squared. So basically those are key things which you have to be comfortable with. So let's see now. The important facts of projectile motion can be summarized as follows. Um, Provided air resistance is negligible, the horizontal component of the velocity uh, remains constant, because there's no horizontal component of acceleration. So since usually we are going to neglect air resistance, so the air resistance is the fact that the air can actually be pulling whatever we've thrown in the horizontal backward, but usually we assume this to be negligible and not to have a lot of impact. So meaning that our horizontal component velocity is going to be constant. Then the vertical component of the acceleration is equal to the free fall acceleration, which is the acceleration due to gravity. Then the vertical component of the velocity and the displacement in the y direction are identical to those of the free falling body. So you might recall that free falling bodies, that's what we were discussing last time on Monday. Okay, then projectile motion can be described as a superposition of two independent motions in the x and y directions. So there, what they're just basically telling us is that when we look at motion, when we look at a projectile motion, it's just basically like two different independent motions occurring in the x and y directions. Reason being, what happens in the uh, horizontal does not affect the what does not affect the vertical, and vice versa. Okay, so before we can start, how many examples are there? We just have got about 3 or 4 examples. Yeah, then we now start forces and motion. So let's see if we can be able to solve all those and start a new topic the next time we meet. So problem solving strategy, projectile motion. So first things first, what you want to do is you want to select a coordinate system. So remember, like I said, right, you're going to have the x axis and the y axis. So you need to know, okay, this question that I'm having, what's going to be my velocity in the y-axis, what's going to be my initial velocity in the y-axis, how am I going to navigate myself around these things. And once you can answer those questions, then you should be in a comfortable place. So those are things which are very, very important. So you want to figure out initial final positions, which is just the same as displacements, and then the velocities and accelerations. And then if you are given a velocity with which the motion started, okay, so you're given, oh, okay, this ball was thrown at this particular velocity with this angle, and yeah, it was thrown at this and that. So then what you want to be able to figure out and what you want to be comfortable with is you want to resolve the initial velocity into the what? Into the y and x components, so that you know say, oh, okay, so the initial velocity in the x axis, it's going to be this and that, whereas the initial velocity in the vertical, it's going to be this and that. And then once you get all those values, all those principles, and you put them together, then you should be in good shape. So that's about it. Anyone having questions so far? Okay, so that's basically how we want to go about that. Okay, let's see. So again, treat the horizontal and vertical motion independently. I think that's something that I've been stressing on for quite some time, to say these motions are what? These motions are independent. Don't treat them the same. They are different things. Okay, what else? Follow the techniques of solving problems with constant velocity to analyze the horizontal motion of the projectile. So constant velocity, because what acceleration is? Zero. Remember, acceleration is the rate of change of velocity. So if there is no velocity, rather, if there is no acceleration, means that there is no rate of change of velocity. So meaning when acceleration is zero, as it is in the horizontal component of the motion, our velocity is going to be constant. What else? Follow the techniques of solving problems with constant acceleration to analyze the vertical motion of projectile. So here basically what is telling you is that really for the vertical motion, that's where you usually have to use those equations of motion that we discussed. But for the horizontal, you're just looking at displacement and displacement and velocity pretty much, right? So that's something that's very, very important. Okay, here's our question. So basically, those are the key components that you have to be comfortable with. So let's look at this example. So this is our example. Okay, should be enough. Okay, yeah. So an Alaskan rescue plane drops a package of drops a package of emergency rations to stranded hikers, as in figure 3.19. So figure 3.19, that's the figure which you can see on the far right. Okay. So now what happens here now is these people are stranded. The plane is traveling horizontally at 40 meters per second at a height of 100 meters above the ground. Neglect air resistance. So why are they telling us to neglect air resistance? Because it's only when air resistance is neglected that we can hold true to our principle of the fact that in the horizontal motion there is no acceleration. Therefore, acceleration is going to be zero and the velocity is going to be constant, right? Okay, so the first question, uh, where does the package strike the ground relative to the point where it is released? So here, what are they asking us? They're asking us to find the range. So what is the range? I said the range is when it's just basically the displacement of a projectile in the x-axis. So for instance, if I throw something in a projectile motion, right? It's going to cover a certain distance or displacement up and okay, and then it's also going to cover a certain displacement down. Now this horizontal displacement is what we call the range. Okay, so when they talk about that, the range, that's what we mean. So then they're asking, where does the package strike the ground relative to the point where it is released? So here what they're just asking us is this. Let's look at and let's analyze this particular question. So here's the thing, you all saw the plane, right? The plane was here, and then these people were somewhere here. Okay, okay, so the ground is here and these where the people are, and this is where the plane is. Now we know that we've been told that the height of this is, the plane is at 1 meters, or rather 100 meters above the ground, and this plane is moving at what? Is moving at 40 meters per what? Per second. So it's moving at 40 meters per second. Now they have to drop this thing. Now what they're basically saying is that this, since this plane is moving, right? So when it releases this portion here, okay, it won't be dropped exactly here. Okay, it's going to move a certain distance. Okay, this particular parcel, even if it's released here, it won't particularly drop right at this point. It will drop somewhere at this point. Reason being, this is something that is in motion. Okay, it's moving, isn't it? So that's something, that's why that's very, very important to take note of. Now, having discussed that, now let's see how we can answer this. So the first things first is that here we are really, really going to be interested to figure out the what's this, the y displacement, right? So we want to first know how long it took this parcel to fall down. Because remember, what are we looking at? What we are looking at, what the question is asking us, where does the package strike the ground relative to the point at which it was released? So it was released at this point, but it fell at somewhere this point, right? So what is this? What did I call this? I called this the range. So we are just definitely finding the what, the range. And what is the range? The range is simply displacement. That's what the range is. The range is just simply displacement in the x-axis. So it's even the velocity is the one in the x-axis. That's the range. So the range is just displacement in the x-axis. So you're just multiplying time and the horizontal, uh, the horizontal aspect of the velocity. Now, when for the velocity of the what? The velocity of this particular plane, we'll figure it out. Now, one thing that we want to find is the time. We need to find the time. Okay, the time which it took this particular package to fall from the plane to reach the ground. Why is it important? Because that determines where on the ground the parcel is going to fall. If this particular parcel takes long, to reach the ground, then means that because the plane is also moving at 40 meters per second, means that even the parcel is going to travel along the ground a greater period of time, isn't it? So that's something that's very, very important to take note of. So Having done that, then one other thing that then we want to understand is we want to understand now the concept of what? The y displacement. So the y displacement is going to be then the time, and then remember we it's now negative because we are now using g. Now we know that this is the change in displacement, and so there is displacement final and displacement initial. So this is now going to be, remember, this parcel was on top. That's what I want to explain. So this parcel was on top, and we are being told that this particular, it was at 100 meters. Okay, so now this parcel moved downwards, right? Moved downwards 100 meters. Okay, so what was the initial position of this particular uh, object? So its initial position was what? Its initial position was 0 meters. Okay, it didn't travel anything at first. Then when it was dropped, since it has to reach the ground, right? So what is this now? This means that we are looking at the final position should be something like what? It So the final position is going to be minus 100 meters. Okay, so that's what we are going to be dealing with. Okay, so we've done that. Then the other thing that we want to figure out is what about the velocity, the initial velocity that this particular object started with. What do we know about this velocity? Remember, velocity in the vertical, we know that this particular plane has got a velocity in the horizontal. But now, when you look at this plane is moving horizontally. So just from figure it out, you would know that definitely there won't be any vertical component. Now, if you'd want to be certain, you then want to use the signs that we have, or rather the equations that we have. So this is going to be initial velocity times sine theta. So when something is moving, remember this plane was moving what? Vertical, or rather horizontally, pardon me, horizontally. So when something is moving horizontal, what's the angle? What's the angle does this have? What angle does this have? So this is the x or y plane. If something is moving horizontally, what angle does it have? The angle is what? 0 degrees. So what you're going to do is, it was moving at what? 40 meters per second times sine what? Sine 0. So what's sine 0? So you then want to find what sine 0. Sine 0 degrees is going to be what? Sine 0 is 0. Okay? Sine 0 is what? Sine 0 is going to be 0. So you see now that it makes a lot of sense to now say that the vertical component of velocity, it was what? It was 0. Okay, but even just from just thinking about it logically, the fact that the plane was moving horizontally, it doesn't really give it a lot of maneuvering space really for it to be able to have vertical displacement. But this is, we've shown it mathematically or in calculations. So now what do we have? So this means we now know that the initial vertical displacement 0 meters, and then we now know that the initial displacement is what? Is 0 meters, and the final displacement is what? Is negative 100 meters, right? So then we can now just factor in all these things into the equation. So this is going to be, okay, just let me just step backward. So change in position, we're going to say final minus initial, then we're going to say initial velocity in the vertical time, and then half acceleration due to gravity t squared. Final velocity negative 100 meters, then 0 meters. Then this is going to be 0, isn't it? You've seen that's 0 there, right? So that's going to be 0 meters per second times time. And this is going to be... Now here is where most people make mistakes. If you've already introduced the negative and you've introduced the g, then you don't have to write negative again. No. If you've already introduced the negative in the equation and you've already written g there, it just has to be a positive like this, because this negative has already been paid for by what? Has already been taken into consideration, that this negative is coming from the fact that acceleration due to gravity is equals to negative g. So that's something to take note of, right? That's where most people make mistakes, right? Because you might remember that from what we were doing last time, because the equations was just having an acceleration, so and uh this point was having a positive, so that's why we are writing the acceleration as what? As negative. But here the negative has already been put, so we just write it the way it is. Makes sense, right? Okay, so then so we write this as meters per second squared and time squared. So this is going to be 100 meters. This one becomes 0. Then that becomes negative 4. So yeah, negative 4.9 meters second squared. And then time squared, right? So just divide both sides. And take note that I'm maintaining all my signs. Okay, so here it's going to be... Okay, let me just create more space for myself. Okay, so then we are going to have that. Okay, so here what you're going to have is... Okay, sorry. The one on top shouldn't be meters per second squared. Pardon me. That should just be meters. Okay. Yeah, that should just be meters. So now let's do the calculation. So that's going to be 100 divided by 4.9, isn't it? So that's going to be 20.4. So this cancels, so you're remaining with what? Second squared. So second squared, you square the time, you square this part as well. So making time is going to be square root of what? 20.4. So square root of 20.4 gives you what? Gives you 4 point, gives you 4.52, isn't it? So it gives you 4.52 seconds. So meaning this is the time that it took this package to fall from where it was on the plane to actually reach down to these people. Now, since we have the time, okay, then we can now figure out what the range was. Remember I said range is just simply the what? The displacement in the horizontal, which is final and minor and the initial, isn't it? And then it's just going to be the horizontal velocity times time. So what's the horizontal velocity? Now, here the parcel was where? The parcel didn't have a vertical velocity that we've already established, but this was on the plane. So meaning whatever velocity the plane was moving with, that's the velocity that the package was. If you are in a vehicle and the vehicle is moving at 20 kilometers per hour, then you're also moving at 20 kilometers per hour, isn't it? Exactly. If the car is moving at 120 kilometers per hour, then you're also moving at 20 kilometers per hour. Then you're also moving at that same speed, isn't it? So then, meaning that for the initial velocity, this particular parcel had the initial velocity, the one at which the plane was moving at, which was what? 40 meters per second times time. Now, what's our time? That time that we found, the time that it took to reach the ground. So now multiplying that, we get what? We get 181 meters. So that's how we arrive at that. Okay. So now, okay, so is everyone clear on that aspect? So now we now go to the second question. So the second question is, what are the horizontal and vertical components of the velocity of the package just before it hits the ground? Okay, so here we're now being asked to what? We are being asked to find what the x and y component of the velocity uh, of the package are at the time of impact. Now it's a very interesting question, a very interesting question in the sense that when we are trying to answer this question, we are now going to get that initial velocity for the horizontal. We know that the vertical didn't have a final, didn't have an initial velocity, right? So the vertical didn't have an initial velocity, but then since it's falling down, remember what I said, in the vertical there is always acceleration, which is acceleration what? Due to gravity, meaning it was this now which was acting on the package. Therefore the final velocity of this package just before impact was not zero, it was gaining a certain velocity as a result of what? As a result of gravity. That's why if something that rose from the roof, or let's say a block rose from the roof and then falls on your foot, it's going to do damage. Why? Of course we talk about potential and kinetic energy, but the fact that it's falling down with gravity, it gains some velocity. Okay, so that's what we are now going to analyze here so that we can get uh, the horizontal and vertical components of the pack of the velocity of the package. In short, they're just asking us to say what was the final velocity of this particular stone just before impact in the horizontal and the vertical axis. So now this is going to be uh, in the horizontal represented by x, we're going to say initial velocity is what? Times cos theta. Initial velocity was what? The package was moving with the same velocity as the package. Then what was the angle? The angle, we said it was cos 0. Okay, what's cos 0? It's 1. So meaning it was 40 meters per second. Again, this makes sense because we said what happens in the horizontal. In the horizontal, the velocity is what? Constant. Okay, is everyone clear? Is everyone clear with this?
Yes.
Okay, sorry, it seems like I'm about to develop a flu or something, but I hope it's still audible. Then now for the vertical, remember we are just basically getting the equation that we used to find to find final velocity. We say it's what? It's initial velocity, but this initial velocity we are now going to write it in what? In terms of the vertical motion. So in short, in case this equation confuses you, it's this one. This one. It's just this one that we'll be doing. So the Vy, that's for the final. This initial times sine theta is just to show that we're talking about the vertical. Then where there was acceleration, that's why we put minus g. So you see here it's going to be minus g. Okay, and then the time there. Okay, so don't get the equations mixed up, right? It's just that here we're just introducing the sign because it's vertical, and we're using the acceleration, we're substituting for g. So that means that when I'm writing 9.8, I don't have to put a negative again. I don't have to put that since the equation has already changed. So meaning that the negative has been accounted for. Okay, so then let's now just plug in the values. So we know initial velocity was this, but because the angle is what, 0 degrees, sine 0 degrees, so again here you see I'm writing it like that. And then time, now the time we are going to put, remember we're now talking at the velocity just before it hits the ground, so we can just take the same time that we calculated earlier on for the time that it took the package to reach the ground. We can just use that because we're just trying to assume what really the velocity would be just before impact. So we can use the same time. So we know sine 0 is 0, so all this is 0. And then this is going to be negative 43 meters. So this is going to be um, so this is going to be negative 44.3 meters. Why does the negative make sense? The negative makes sense because this particular object is now falling. Okay, and when it's falling, what's the direction? The direction is downwards. Since the direction is downwards, meaning that's where the negative makes sense. So meaning here we now have the horizontal component and we've got the vertical component as the question asked us. Okay, then let's now look at the third question, which says find the angle of the impact. So here is just basically like we're just uh, revising on our vectors, right? Where we've got the components and then we just have to apply that. So for C, we've got our y component, which is this, and then we've got our horizontal, which is this, isn't it? And then so now here we need now to find the angle of impact. We know it's tan theta, and then it's going to be what, y over this. So this is going to be tan theta, it's going to be minus 4.3 meters per second over 40 meters per second. Okay, so this is going to be what, tan negative 1.11. Then this is going to be tan inverse. Now this is something that I want to take into consideration. With these components that we have, remember we're talking about vectors, right? So we want to know really in which quadrant is our angle in, because that will help us figure out really what will be the magnitude of our angle. So that's why if I wanted, I would have whereby I don't include the negative in the calculation, because now that I've included the negative in the calculation, what this basically means is that the answer that I will get, okay, the answer that I'll get, it's already been converted to what, to a certain number, right? So much that it's going to be the actual answer, even though it can end up negative or not, but it will end up being the same answer. So I'm going to do this in two ways so that I can just clear up this, right? Okay, so now, so I can do this where I'm going to have an answer which is going to be what, negative 48 degrees. Now I know that negative 8, 48 degrees is just because this is just an angle which is negative 48 degrees here. So meaning to get the actual angle, I have to what? Add 360. So then I'm going to get what's going to be my angle. So my angle is going to be so that's going to be okay. Just give me a moment. So it's going to be 360 minus 48, right? So that's going to be 312. Okay, so that's the answer. So now you see, so but there's another way. I think that's the method that I actually showed you when we are doing vectors, where you saw here where we are the negative, where I don't put that negative. I just write all the numbers irrespective of what the numbers I have. I just write them as what? I just write them as positives. So now what that will do when I write all the answers as positives, what that is going to give me is uh, so what that is going to give me when I write tan 1.11. Okay, so inverse tan point, so that's going to be about 48, right? So I'm now getting a positive answer. So I've gotten a positive answer, but now when I write it in this way, now that's where now I have to take note of what quadrant is my answer in. So now just a revision on these vectors, right? So this means that let me figure out now which quadrant my answer was in. What was my x-axis? Was it positive or negative? So I realized that, oh, my x-axis was what? Was positive. So if it's positive, meaning my x-axis is here. Then what about my y-axis? My y-axis was negative. Okay, so meaning that my vector, my resultant vector is here. So you see that it makes sense that the angle that we found was what? Negative 48. Because negative 45 simply means that instead of going positive like this, you only get a negative answer when you go directly from the positive x-axis, you start going down. That's when you start getting, when you go clockwise, right? So what this entails is that uh, this particular answer, I know that this answer is what? This answer is in the fourth quadrant. And what do I do? So since when I don't put the negative there, my answer is just going to be 48 degrees. Now I know that it's in the third quadrant. And what do you recall we said? When you find an answer in the fourth quadrant, what do you do? You're going to say, okay, it's in the fourth quadrant, and what I've found, because what the 48 degrees I've found, it's this angle here. So what do I do to get the actual angle coming from this, like this? So I'm going to what? To subtract that. So which is going to be again 312. So I just wanted you to know that you can do it both ways, right? But the key thing is just understand, and the answer that you get, let it make sense to you. Okay, like let the angle make sense to you. Ensure that you don't have an angle that is not adding up, right? So ensure that the angle that you get is making sense to you. Okay, any questions? Yeah, so let's look at the next. So basically, that's how you can answer these kinds of questions. So let's now look at long jump. So, okay, the question is here. Yeah, so a long jumper, we see there in figure 3.20, which is just on the far right, leaves the ground at an angle of 20 degrees to the horizontal at a speed of 11 meters per second. Then we are then asked, how long does it take for her to reach the maximum height? Okay, so if we are being asked how long does it take for her to reach the maximum height? So again, remember, the horizontal and the vertical motions are independent of one another. Okay, they are independent of one another. So what does this entail? So this entails that since here we are being asked about how long it's going to take this particular person to reach the highest point. So just basically look at it as the vertical motion alone. Look at it independently. It's just the same as someone throws something at an angle of what? At an angle of 20 degrees, throws it at an initial velocity of what? At an initial velocity of 11 meters per second. And then you're just being asked, what? How long is it going to take for it to reach the what? To reach the highest point. Now here is what's interesting. What do you know about the highest point? You know that at the highest point, the velocity in the vertical is going to be 0. Does that make sense? So you know that that particular velocity, what? That particular velocity is going to be 0. So what then you're going to do is you're going to get the equation for vertical velocity and equate it to 0 and then solve for time. Does it make sense? So the equation for velocity is this. So this is going to be this. That's going to be initial velocity times sine theta minus gt. Okay, again remember this is just the same as this, is just that we've just changed again, just like I explained in the earlier example, right? No need to go through that again. So now what's the initial velocity? Initial velocity is 11 meters. Now remember, this initial velocity is just the initial velocity overall, not at an angle or any, no. In fact, it's called a speed, right? And it's actually called speed. And remember from the earlier question that we've calculated, speed is when you get the x component and the y component, and then you get speed, isn't it? So meaning speed is not in any it's a sum of those components, just like we did in the earlier example. So what's the angle? The angle we've been told it's thrown at 20 degrees. And then what's our g? That's 9.8 meters. Take note, I'm using all the units. Then we're now going to time. That's what we are looking for. But this is equal to 0. Why is this equal to 0? Because we are looking at the question says how long does it take for her to reach the maximum height. We know that at the maximum height, the velocity in the vertical component is going to be 0. So that's why we're equating this particular equation to 0. So we've gotten that 0. Okay, so we've gotten that 0, and so we can be able to work it out. Okay, so then what we are going to do is we can then say, so let's say sine, okay, so let's say sine 20 times 11. This is what? This is about 3.7622 meters per second. And then this is 9.8 meters per second squared time. This one is just a simple equation. Okay, so give me a moment. So this is just a simple equation which we're just going to move this to this side. So this is going to be 9.8 per second squared, 3.7622 meters per second. Then divide both sides by that, and then this side by that. Okay, so you see that those negatives have cancelled out, right? And this makes sense because you can't have time which is a what? Which is a negative, right? So up to this point, do you have any questions? Any questions up to this point? Yeah. So up to this point, we are then going to have So this is going to be 0 point, this time is going to be 0.384 seconds. So that's how you would answer that. So, and then now, the other question then says, then the other question, which is D, which says, what is the maximum height? So since we've got the time, this should be a straightforward thing, isn't it? Since we have the time and we are just looking for the what? For the horizontal velocity. Oh, sorry, vertical displacement. So this is the equation we are going to use. So it's going to be sine theta and then the time it took to reach the maximum point, which is what we found in the earlier example. And then we're going to have g then time squared. So in case this equation confuses you, it's the same equation as this. Let me just write it this way so that you can at least remember it, right? So it's just that we've converted it to suit the vertical. That's why we've put the sign, and then the gravity. That's why we've put the g and the negative there. So since we have the initial the speed there it was 11 meters. The angle it was 20 degrees. The time that's what we found in the earlier question, 3.8 seconds, and then this is half. So the half is then going to be, so the half is then going to be, so then the half is going to be for the 9.8. Okay, let me just move it a little bit down so that I can write properly. Yeah, so then this is going to be meters. Take note that I'm putting all the units, and then we also square the time. Okay, seconds and square. So what are we going to get? So doing all these things, we are going to get the value of 0.722 meters. So meaning when this person does the jump, she's going to take 0.84 seconds to reach our highest displacement or our highest vertical distance, right? And so so that will be how high she would have jumped. And this makes sense because those people can really go high, but not very high. So this number pretty much makes sense. And so because of time, I will be able to end here. So we'll continue from the uh, question C and D the next time that we meet. And then once we do the other examples, then we can start pretty much the next topic, forces and motion.